Hi again. Here we go, finishing up chapter 11. The last little bit here is stuff we've already kind of talked about, but we need to talk a little bit more. Chapter 11 is all the stuff we've been doing on chemical reactions, and the last section talks about reactions in aqueous solutions. And they start off with a brief discussion about cave formation, which of course we have a lot of caves around here, which is kind of cool. So if you've been to Moaning Caverns or any of the other caves, or maybe you've been lucky enough to been to Carlsbad Caverns, um, cave formation is pretty interesting, and it all happens in solution, and that's what this is all about. So we have lots of limestone in this area, and as the water drips through, it dissolves some of it, and yeah, it's pretty cool. So watch that video that I have in the assignment. So net ionic equations. What does a net ionic equation show? Well, you probably are familiar with the term net paycheck or net pay. Maybe you've heard of that before. You know that things are taken out of your pay if you have a job, which I hope some of you still do, for taxes and Social Security and things like that. So you don't get your $15 an hour or $10 an hour. You get a reduced amount. So you take out some things. All right, so ions, have charges, and equations is what we've been doing. So here we go. Complete ionic equations are equations that have all the possible ionic, they call them species, but all the dissociated free ions. So this is a reaction that I did for you in our lab that we just completed. Silver nitrate and sodium chloride, aqueous, they're both soluble in water. And so these two compounds, when you put them into water, break apart into ions. Then those ions have a chance, this is the innies and outies things, those ions, the positives from one can go with the negative of another. The positive silver can go with the negative chlorine and can form new compounds. Some of those compounds are not soluble, they form solid precipitates, and sometimes the ions stay soluble in water and stay aqueous. So if we were to break apart silver and nitrate into their pieces, we get positive silver ions and negative nitrate ions. The sodium chloride likewise breaks apart into positive sodium ions and negative chloride ions. However, we know that silver and chlorine make an insoluble solid. There's no ions there. But sodium ions are always soluble, as are nitrate ions, so they are still suspended in the water. You won't notice them. The white precipitate that forms is the silver chloride. So why write all these stinking ions down if they're not doing anything? So one thing that chemists do, because we're minimalists at heart, is try to get the extraneous stuff out of the way. So if an ion appears on the reactant side and the product side of a reaction, then they're not involved in the actual reaction. They're spectators. They're just hanging out on the sidelines watching what the other stuff's doing. So a net ionic equation is only going to show the particles, the ions that actually make something new. They're the ones that form the precipitates. Those are the only ones we need to write down in a net ionic equation. So the ones that form a precipitate are the ones that actually cause a reaction. Now, you also have to watch out with ionic compounds. Again, you have to make sure that mass and charges are balanced, same mass on both sides, zero charge, all that kind of stuff. So if you paid attention in January and early February, you're going to be having an easy time with this. So here's our equation again. Silver, nitrate, sodium, chloride, silver, chloride, sodium, and nitrate. Since the sodium chloride and the chloride ions are the only ones doing something, when we cut to the chase and get rid of the extra fluff, we just can write Ag plus and then parentheses AQ indicating it's in solution. Cl minus, parentheses AQ, makes silver chloride solid. Now, this is a nice easy one to do because there's no coefficients needed. +1, -1, all done. Okay, but it gets more complicated, obviously, you know that. This is another example of two solutions forming an insoluble precipitate, iron chloride, iron 3 chloride, and potassium hydroxide. And we're going to end up with iron hydroxide forming. So how does that look? Well, the first thing you're going to do is write the complete ionic equation for the reaction showing all the ionic, all the bits and pieces together. So iron 3, Roman numeral 3, gives a +3 charge. You would need, I'm sure you know, 3 chloride ions to get that substance to 0. So there's our iron 3 chloride, all the pieces. Potassium and hydroxide go together 1 to 1. However, the iron hydroxide that forms the precipitate is going to need 3 hydroxide ions, which means we're going to need 3 potassium ions, which is good because we need a +1 and a -1. We need equal numbers of positive potassiums and negative chlorides. So this is a complete equation, all the ionic species plus the precipitate. But again, only the iron 3 and only the hydroxide actually do something. Okay, so potassium and chloride, those are always soluble. They're almost always for chlorine, not absolutely always, like we just saw with silver chloride. But the potassium ions are always soluble. And so our net ionic equation is going to have iron 3 ions, 3 plus charge, with 3 hydroxide ions, 3 minus 1s. And then remember, the hydroxide has to go in parentheses. It's a polyatomic ion. We need to wrap it up. And this 3 subscript tells us there's 3 of them. Notice I've seen this a lot on your work. People have been putting the Roman numeral inside the chemical formula. That is not where it goes. It only goes in the name. All right, predicting precipitate formation in double replacement reactions. This is tricky, and this also is kind of related to reactivity, but there's a few general rules that'll help you, especially in this early basic work. And this is in a table in section 3 of chapter 11. So I put out a table. I'll put it into the assignment today as well in case you can't find it. But I have a slightly different table than this, but this is a good start. So any salt, remember a salt is just something that's an ionic compound, usually an alkali metal with a halogen, but not always. Any alkali metal or ammonia compound will be soluble in water. So lithium, sodium, potassium, rubidium, ammonia, remember they all have a +1 charge. Any salts with nitrate and chlorate are also soluble. Remember they both have -1 charges. Sulfate salts, that would have a -2 charge, is often soluble, but not always. There's some exceptions. Chloride salts are mostly soluble. The glaring exception is silver and lead 2, and also mercury 1. Again, this is a -2 charge for sulfate, -1 for chloride. So those are all soluble. The biggest exceptions are silver, lead, mercury, barium, strontium, and calcium as far as being insoluble within these possibilities. Again, silver, lead, and mercury here as well, mercury 1. And then finally, almost all carbonates. Remember, carbonate is a -2 charge, phosphate's a -3 charge. Chromate, sulfide, hydroxides, almost all of them are insoluble. They do not stay dissolved, they precipitate. All right, so prediction. What's going to happen if a sodium carbonate solution is mixed with a barium nitrate? Remember, nitrates are always soluble. Sodium compounds are always soluble. Most carbonates are not soluble. Most barium compounds are not soluble. So again, this is a double displacement. Ionic sodium carbonate, ionic barium nitrate. Notice the coefficients here to balance the charges, +1 twice to cancel a -2, +2 and 2 -1s. Those compounds then, we're going to have our little ines, barium with carbonate, remember positive cations first, and outies, sodium with nitrate. Well, you should know sodium and nitrate are going to be soluble. If anything's going to happen, it's barium. And let's go back in here. It says carbonates. Almost all of them are insoluble. Okay, so hopefully you predicted barium carbonate. And I guess I should have had on here the net ionic equation. So you'd have a Ba2 plus aqueous plus CO3 2 minus aqueous produces 1 BaCO3 S or PPT in parentheses for precipitate. That would give us our net ionic equation. Sodium and nitrate are the spectator ions. And that is quite enough of chapter 11. Take care.